Let's give a minute or two for people to log in. Okay. All right, we'll still get more people logging in, but all right, we're going to kick this off. Again, welcome to another great session at LRVS. This is the EMEA portion, and really thrilled to introduce Alessandro Paccagnini. Dr. Paccagnini with Mecoil. We were just reminiscing about our time in the UK, and it's so good to have you here at LRVS talking about wear debris analysis, helping some RCA of serial failures in train transmission. So without further ado, Alessandro, I'll hand it off to you.
Oh, thank you, Josh, for your introduction, and welcome everybody. I'm speaking from Italy, Florence. Mecoil is the company I work for. We are an oil analysis laboratory with more than 30 years of experience, based in Firenze, as you can see here. So oil analysis are our main job, and in the past, let's say, 5 years, we've been gaining much experience, much more experience in railway transmission analysis. So I'm going to share you something that we have discovered in this presentation. Let's say that rail transportation is very important in many places in the world now, especially in Europe, North America, and the Far East. It's probably the greenest way to transport people and freight, has a very high social relevance and high asset value, and the procedures for operation, maintenance, and overhaul are very standardized throughout the world, I would say. And so one can do condition monitoring on the train in many machines in the train, diesel engine, hydraulics, electric motors, air compressors that are used for braking, couplings, they're lubricated with grease, and also gearboxes. And we found that these gearboxes are the most critical machinery in this application. These are quite simple machinery, but very high performance with very high power applied, up to 1 megawatt per gearbox. But the amount of lubricant is very small. Let's say normally not more than 10 liters of oil. There's no filtration usually. There's no pump, no oil cooler. There's very often a magnetic plug. They use normally very high performance synthetic lubricants, and they have fixed and scheduled maintenance intervals based on mileage, so on kilometers. Oil analysis on this kind of machinery is very similar. It has the same principles than other applications. So we look for fluid conditions, contamination, and wear debris, and we have found that, let's say, normal fleets, these lubricants are very stable from a fluid condition point of view. So there's normally not much oil aging, not much oil, let's say, oxidation. Viscosity is very stable. Additive is not very going old. Okay. Also, contamination, except some rare cases, is somehow, let's say, controlled. But where processes are the most important things to look after. And so how do we monitor these wear processes? There's the normal techniques used for wear monitoring, like atomic emission spectrometry that we do with the spectroil rotating disc electrode. We use the ferrous debris quantification by magnetometry using the ferrocheck, and also optical particle counting, and also we can use optical microscopy, as I will show you later. We did this job with many thousands of gearbox oil samples, let's say, with homogeneous families of gearboxes and the same type of service. Okay, so elemental spectrometries and ferrous monitoring are the routine for this kind of application. Particle counting is something that we do often, but not always, because it's not there's no filter in these kind of machines. Okay, and microscopy is normally used to confirm the anomalies that we sometimes find. As you can see here in the left part of the slide, I show you the results of a population of samples where we could, let's say, identify very specific limits for this family of transmissions. And now we speak about different kind of gearboxes. This is a regional train gearboxes. Okay, a sort of a fleet of these gearboxes, homogeneous surface, all the same. We did a sort of screening test, one shot. We did not have any trend on the history of these gearboxes, so the customer did not do any particular, let's say, condition monitoring techniques. So they asked us to do a sort of screening test throughout the population of the gearboxes, and we found that there was a sort of rule. The normal samples regarding iron concentration and total ferrous, okay, here, but there was a very high population, significant population, having a very high amount of ferromagnetic particles in the lubricant. Okay, so these are, let's say, thousands of ppm of iron and magnetic particles. So this is not very normal, not to be considered normal. And another strange thing that we found is that this iron concentration and ferrous particle concentration did not have any correlation with the oil mileage. So it seemed not to correlate with the length of service. Okay, so all the high ferrous oils were in the first half of the oil service. Okay, so the oil is supposed to last for 300,000 kilometers, but all the high ferrous samples were in the within, let's say, 150,000 kilometers. Okay, and some of these transmissions suffered from severe bearing failures. In these samples, we did also some microscopy, and we found very large, as you can see here, large particles. Everything was, let's say, iron, magnetic iron here. And also here, these are the routine samples, okay, the screening samples. And we found mostly these particles were very, the platelets, okay, the sort of platelets, but we also found some chunky particles here. So some of these, the most severe problems were problems in this population of gearboxes went out to the OEM for inspection. Okay, and when they opened the gearboxes, these gearboxes were affected by a very high amount of ferro debris. You see here this small mountain of gray material. This is the ferro debris. Okay, but in this condition, the bearings were very affected, very worn out. but the wheels were in very good conditions, okay? And also in many gearboxes, there was a water contamination, although we did not find any water contamination in the routine samples before. And this is the condition of the bearing. You see very severe wear on the brass cage here, and very modified geometry and very worn out rollers, okay? We also did some observation and measurements on these rollers, and you see the roller diameter was very modified, so they could not work correctly anymore. And there was also many signs of denting, very large holes on the roller surface. Okay, this is normally due to the presence of large particles in the oil. We also did some lubricant analysis on this gearbox. This lubricant was collected during the inspection. Okay, and we found that there was very high fine metals present in the lubricant. Okay, you see the copper, the zinc due to the wearing of the brass cage, and the ferrous metals. Okay, but lubricant was in good conditions. Okay, there was some kind of solid ambient contamination and very high water contamination, 30% in this gearbox. We also did some analysis on the debris found in the bottom of the sump, as you can see here. And what we did here was that we wanted to separate the fine metals that we looked after in the lubricant. We wanted to separate the larger particles. So we did some wash with heptane to eliminate the lubricant, and also disaggregated using an ultrasound bath, and filtered all the particles on the steel mesh of various sizes. And this is here we show the mesh of 200 microns, okay, which is the one that we used the most. And in this debris found in the gearbox, there was two main kind of particles, okay? There was the flakes that are laminar in shape with irregular and clear edges, somewhere striped, as you can see here. This might be due to wear, these particles, okay? But there are also very large chunks, very, let's say, also high, rounded edges, irregular faces. These are very hardly due to wear, okay? This is normally not referred to wear, okay? We also found some paint flakes, no overheating, no rusting, and no sludge. Sorry. Okay. Another gearbox, this is number 2, the number 2 example. We did also, in this case, some previous sampling during March, and in July, we did some, our customer did a gearbox inspection. And here, the lube oil analysis was giving erratic samples, but our customer took, let's say, samples from the sump of the debris from the sump bottom and outer side of the labyrinth seal. So this is the debris from the sump bottom, and we find the same particle types. This is a different gearbox than before, okay? The same particle types, as you can see, the red dots, the very large chunks, and the green dots are the flakes. On the same particles, we also did the SEM microscopy, and we found the same, obviously, the same two types of particles. So looked like that the two types of particles were made of more or less the same metal, okay? All, let's say, low alloy steel with slight signs of oxidation. This is the debris collected from the outer of the gearbox, okay? So this is in the area near the labyrinth seals, okay? And we found here the same chunky, globular, chunky ferrous particles, okay? The difference here is that these particles from the outside of the gearbox, they were showing signs of rusting on the particles. As you can see here, there are some reddish brown color. This is the SEM analysis on the labyrinth seal particles. Okay, you see the oxidation here. Oxygen concentration is very much higher than the particles found inside the gearbox due to the rusting. Okay, so it looks like that we find the same particles in the outside of the gearbox and in the inside. Okay, these globules, the very large globules, are present both on the outside and the inside. So this might mean that these ferrous globules may come from the outside through the labyrinth seals. Okay, this might be abrasive powder. So our customer hypothesized that it could be abrasive powder, and they gave us a sample of the abrasive powder that he used during overhaul. These axles are, let's say, taken out of the train, and they are sandblasted with this powder. And this process is robotized, is automated, okay? And this is due to the need to remove the paint and to renew the paint on the corrosion protected paint on the axle, okay? So we tested this powder with the same techniques, okay? You see the metal mesh, and also with the SEM EDS microscopy. And we found a composition that was quite similar, very similar, I would say, to the one that we found on the particles from the gearbox. So this is a sort of comparison between the three particles types that we found in these gearboxes. The abrasive powder, the edgy particles are irregular, chunky, okay? The gearbox labyrinth seals, they're rusty but rounded because they've been hitting the gearbox and the axle, okay? And in the gearbox, we found the same rounded, irregular, chunky but not rusted particles. So let's summarize what we found. That there was an axle blasting during scheduled overhaul. This is an automated process, and this abrasive powder used for this sandblasting was found in the lubricant in the gearboxes, okay, of these damaged transmissions. Before the gearbox inspection, these gearboxes were sprayed with water to wash them, okay? And also the sprayed water could find a way to get in the lubricant, so that they found, upon opening the gearboxes, they found the lubricant contaminated with water, okay? So it looks like that if it's not correctly programmed, this automated blasting can also affect the labyrinth seals. And so in these very delicate areas, this paint removal might be needed to be carried out manually. Also, the standard norms recommend to do this manually. So it happened that this abrasive powder in the lubricant caused probably an abnormal wear process with metal surface geometry alteration, as I showed you on in the bearing photographs. And in this process, the large particles, the globules with the red dot, they sometimes got squeezed, fragmented, and remolded by the bearing's motion, and they generated these very large flakes, the very large laminar particles. And this initial severe wear has probably caused the release of very high amount of small wear particles, let's say the one that normally detected with routine analysis tests, as you can see here with the blue dots. This is something that we didn't find only in in this kind of regional train gearboxes, but we also found it in many other types of railway gearboxes. So it looks like that this problem with sandblasting, not very precisely, let's say, set up, looks like it's a common problem that happens during the overhaul of these axles and their gearboxes. So probably a more accurate blasting process could be welcome. Okay, you agree? So let's say what we wanted to show you here was a sort of mixed approach on condition monitoring on these machines, because our routine testing was able to catch up with the special conditions, with the abnormal conditions in train gearboxes, but finding the root cause was not satisfied by the normal and routine tests. So it required an in-depth analytical approach for particle characterization that we needed to focus on large particles only. And this was achieved by using mesh separation, metal mesh separation, as I showed you, combined with modern microscopy techniques like focus stacking optical microscopy and SEM microanalysis. Okay, this is it. Do you have any question? Thank you.
Thank you so much, Alessandro. And I think we have loads of questions coming in. And so one of our friends, Mr. Thenaraj, has a bunch of great questions. Looks like he was following you in detail. I don't know if you could see them. But he starts off by asking if it's possible to check greater than 500 ppm iron in ICP.
Yeah, it's possible to check more than 500 ppms. Like let's say that at this very high concentration, we don't expect the results to trend very precisely. Okay, because also sampling can be very, let's say, effective on the results. Okay. But let's say it's possible to check with the RDE, especially, it's possible to check this high concentration. ICP, I'm not sure. Okay,
the RDE will identify that high. Okay. And another question was, if there's more than 30%, water in the oil, were there any water-oil separation issues? Any corrosive debris?
No, we didn't find any. We didn't find any corrosion, and the reason for that is that during gearbox service there was no water. Okay, so we didn't find any water during the routine testing. Okay, and the 30% water in that gearbox was due to the fact that in the service laboratory, let's say, they sprayed the gearbox with water before opening it. Okay, so there was no water probably before this operation.
Okay, got it. And the washing aspect didn't contaminate it. Okay. And another question was, so by SEM EDX, no non-ferrous materials noted. And I think the question is cage material found non-ferrous?
Yeah, yes, that's not non-ferrous. That particular, let's say, particles that we analyzed with the SEM microscope was the sieved particles. Okay, so it looked like the non-ferrous, the yellow alloy brass particles were much finer than 200 microns. Okay, so they were in the lubricant, but only as fine particles.
What was your determination to use these different analytical means, right? So why choose those particles to identify with SEM?
No, I don't know. I don't know. I don't know the material of the SEM. We didn't attend to the gearbox inspection.
Oh, okay, got it. Okay. And so another question: the labyrinth seals are they made of non-metallic rubber? And then how could they be identified by SEM?
In the analysis of those particle samples, there were also in some samples there were also some non-ferrous, but very sporadic. Okay, we found some particles that were non-metallic. That could be the labyrinth seal material.
Okay, got it. And then using SEM, do you then take the elemental composition and compare it to those known parts, right?
Yeah.
And you've got that from the OEM, I presume, in terms of what each material specifications of the.
No, we didn't find. Let's say the SEM was carried out also only on the larger particles. Okay, so these large particles are likely to be mostly the abrasive powder particles that are very chunky when they are somehow non-remodeled and then squeezed, but the same composition. Okay, let's say in oil analysis samples we also found some alloy metals like chromium, nickel, and manganese, but those were present mostly as fine particles. That was not the cause of the wear, but the effect.
Understand. Okay. Another question about abrasive particles, during the axle blasting, which are normally flushed out, right? How did that get into the gearbox sump? Do we know?
Yeah, it's probably due to the fact that the blast was directed on the labyrinth. Okay, and this is the problem. This is the main problem with this application, because let's say at least Italian norms standards on this tell you that in that areas those should be blasted by hand. The paint should be removed by hand, by brushing or sandpaper, let's say. Okay, not by automatic blasting. Okay, so maybe let's say the labyrinth seals are not made to withstand that power of sandblasting, automatic.
That makes a lot of sense. And we have a question from our friend Bruno in Brazil. Has your client tried any online monitoring techniques to prevent machines to be out of service? So rail companies in Brazil suffer from some of these same problems.
We don't know. They have we don't exactly know. I know that this kind of gearbox has a sensor that I think it's connected with the magnetic, let's say, plug collector, particle collector. Okay, so I think there's a sort of alarm or possibility to monitor this, but I don't have any results on this. So I don't know if there were some alarm on this sensor. So actually, they needed to analyze the lubricant during the normal service to see which bigger gearboxes had the problem.
Understand. Excellent. Okay. Alessandro, this was an amazing presentation. A very, very detailed explanation of these failure modes on the train gearboxes. So we certainly appreciate that. We got some thank yous coming in from the audience. So I wanted to thank you, Alessandro, and then of course all of our attendees here at LRVS.
thank you also for your attention and your hosting. Okay.
Yeah, no problem. All
See you
right.
in Firenze. Ciao, ciao.
Yeah, yeah. Ciao. Bye all.
Bye.